So lesson 4.6 today, we're going to continue our work with equations and inequalities, and they're going to continue to have variables on both sides. But today we're going to look at some very specific situations that either always or never occur. So the big idea, some linear sentences, which is what these are, have either no solution, or for others, they're true for all real numbers, meaning any number could be plugged into the equation and it's going to be true. So instead of x equaling just one number, or maybe x being any number greater than a certain number, it's possible x can literally be any number, or x can't be any single number in the world. There is no solution that makes it true. So we're going to look at those specific situations today. So starting with example number 1, we've got this equation. First of all, I've got some simplifying to do on the right side, so I'm going to take care of that first. So I'm going to get 50w plus 5, and on this side I have 50w plus 5. Okay, so right off the bat, that should look a little weird, right? We got the same thing going on both sides. So if we were going to just actually go through the mechanics of solving this, we want to eliminate one of these variables. So we're going to minus, it doesn't really matter which one. They're both the same size. So we're going to minus one of the variables away, but what ends up happening is actually both of them go away. And we end up with 5 equals 5. Now we need to analyze that statement. Is it a true or a false statement? Now clearly 5 does equal 5, so this is a true statement. So what this means is that our variable w can be anything. Since we have a true statement, 5 equals 5, if we went back and plugged in any number we want for w, both sides of this equation are going to come out equal. And that should make sense because it's very clear that the left side of the equation is the same as the right side. So if you plug a number in on the left and the right, you're going to get the same thing. So w can be anything. There's an infinite number of solutions. And this is one of those situations where this is true for all real numbers, and there's a symbol for that. All real numbers, it's called the double bar R. So it's a capital R, and it's got that extra bar coming down. So you can just put this symbol, this is good enough. You can write an infinite number of solutions, or you can just put the symbol for all real numbers, and that will work. All right, so what does this look like in an inequality? So if we come over here, we've got some simplifying to do. We're going to combine the 80k and the minus 38k. So if I put those together, that's 42k. And I still have 42k on this side. So you can start to see what's happening. So now I'm going to subtract, either one. They're both the same size. So I'm going to minus 42k from both sides, and it's going to cancel on both sides. Now, when a complete side cancels, we've talked about we got to put 0 there. So 0 is less than. This side, all I have left is 6. So I need to analyze that statement. Is 0 less than 6? Yes, that's true. So in this case, k can be anything. There's an infinite number of solutions. And the shortest, most concise way to write an answer here would be to say all real numbers. Any real number, positive, negative, fraction, decimal, even 0, okay, we'll make this a true statement. All right, so sliding down, that's when there are an infinite number. So what about when there's actually no solution at all? What's that going to look like? So you may think, well, if I have the same thing on both sides in terms of my variables, and I know they're going to cancel, then that means anything can go in because that's what I saw here. But be careful. There's definitely another way that things can happen. So when I look at this, I don't have any simplifying on the left and the right. So since I do have an x on the left and an x on the right, I want to get rid of the smallest one. They're the same, so it doesn't matter which one you technically have chosen in your head. You're going to be subtracting 5x on both sides. And they cancel. And we get 30 equals 28. So the answer here is not all real numbers because we have to analyze this statement. Does 30 equal 28? No, this is a false statement. So what does this mean? That means there's no number that will make this true. So it doesn't matter what number you plug in for x. If you plugged in 0, the 5s would go away, and it says 30 equals 28. Well, that's not true. Well, if you plugged in 1, 5 times 1, add it to 30, that's 35. 5 times 1, add it to 28, that's 33. Those don't equal. So it doesn't matter what number you plug in for x on both sides. This is not going to be a true statement. So you can write a couple different things. You can say there's no solution. You can write that out in words. We talked about you can show this symbol, and that's also referred to as the null set. And the last way is kind of these set of parentheses, brackets. Okay, normally you'll see this with an answer in the middle of it, or an actual number. But since there is no answer to go between there, this is called the empty set. So it's just another way to write this. So most people tend to choose the null set symbol, and that's fine. But any of these are good answers. No solution, the null set, the empty set, they all mean the same thing. So let's look at an inequality. First things first, you always want to simplify if you can. So 4n plus 44. Bring it all down. Now, I've got a 4n on both sides. I'm going to cancel them out. So they both go away. And now it says negative 6 is greater than 44. So I need to analyze that statement. Is that a true statement? Is it a false statement? Well, clearly negative 6 is not greater than 44. So that's false. So it's the same thing. No solution. There's no number you can put in for n that's going to make this a true statement. And so any of these symbols will suffice. All right, if we turn this over, how does this show up now in a word problem? So Sarah and Rob just got new jobs at the same company. Sarah starts at $30,000, and she's going to get a raise of $5,000 every single year. So every year she's going to make an extra $5,000. So next year she'll make 35, and the year after that she'll make 40, and then 45, on and on and on. Now Rob's starting wage is $28,000, and he's going to get a raise of $5,000 a year. So he starts at 28, and then his salary is going to go up $5,000 every single year. How many years will Sarah and Rob earn the same pay after how many years? So you may know the answer right off the top of your head, but we'll see what this looks like as an equation. So she's starting at 30,000, and she's adding 5,000 every single year. I'll put Y for years. That makes sense. We want to know, when does that equal Rob's pay? So Rob's pay is starting at 28,000 and increasing by 5,000 a year. So clearly, if they are increasing by the same amount every year and they started at a different amount, okay, they're never going to be the same. So how does this work out mathematically? You've got variables on both sides. So we're going to clear out the smallest one. They're both the same, so that's what we're clearing out. They're going to go away, and we are left with 30,000 equals 28,000. It's false, not true. So there is no solution to this. There's no number of years that we can plug in to make this a true statement. And so with a word problem, it's always good to write your answer in a full sentence. So Sarah will never have the same pay as Rob.